All right, today we're going to be detectives. We're stepping inside a chocolate factory to solve a little mystery, and in the process, we're going to uncover one of the most powerful ideas in all of statistics. So let's get right into it. So here's the scene. You've got this massive industrial machine that's churning out thousands and thousands of chocolate bars. But there's a problem. There's a bit of a disagreement brewing on the factory floor.
And that is the big question. See, everything seems to be running just fine, but a worker who's been on the line for years, well, they've got a hunch that something's not quite right.
So you've got two competing stories here. On one side, you have the official specs for the machine. It's calibrated, it's set, it's supposed to be making bars that weigh exactly 5 grams on average. But then you have the worker, relying on their experience, saying, you know what, I don't think it's hitting that number anymore. So who's right? How do you figure this out?
Well, what's the first thing you do? The most obvious approach, right? You've got to go check the actual chocolates coming off the line.
So let's just follow our gut here. It's a simple 3-step plan. First, we'll just grab a handful of chocolate bars. Second, we'll weigh them all and figure out the average. And third, based on that average, we'll make our decision. Seems totally logical, right?
And here we go. We take our sample, we run the numbers, and the average weight is 4.9 grams. That is definitely less than 5 grams. It really looks like that worker knew what they were talking about.
So it seems pretty obvious. The machine's broken. We gotta shut down production, get the engineers in here. I mean, the evidence is right there. It's an open and shut case. Or is it?
And this is where statistics comes in and makes everything so much more interesting. Because that simple, intuitive conclusion we just made, it might be completely wrong. We've overlooked something really important about how samples actually work.
To really wrap our heads around why that 4.9 gram result is so tricky, let's step away from the factory for just a second. Let's imagine we're in a classroom. A teacher wants to know the average age of her 16 students, but she only has time to ask 3 of them.
Okay, so she grabs her first random sample of 3 kids, she calculates their average age, and she gets a number, about 233 months. Pretty straightforward.
But just for kicks, she decides to take a different random sample of 3 students. And whoa, look at this. The average age for this group is 255 months. That's a huge difference from the first sample.
Let's do it one more time. A third random sample of 3 students. And now the average is about 228 months. It's different yet again. What in the world is going on? And this gets to the absolute core of the problem. Just by pure random chance, every single sample you pull from a population is probably going to be a little bit different. And because of that natural variation, we can't just blindly trust one single sample to tell us the perfect truth about the whole group. That 4.9 grams we got from the chocolate bars, it might have just been a fluke of random chance. This brings us to a really important idea. These numbers that we've been calculating, the 4.9 grams, the different student ages, they have a name. They're called statistics, and a statistic is just a number you get from a sample that you use to try and estimate the true value for the entire population. It's an educated guess.
So, if every sample is different, and we can't totally trust any single one, are we just lost? Is it impossible to figure anything out for sure? No, not at all. We just need to zoom out and look at the bigger picture.
Because here's the amazing part. Even though any one sample is unpredictable, the behavior of lots of samples taken together is actually incredibly predictable. The randomness starts to organize itself. So just imagine we did this thousands of times. We took thousands of samples, calculated the average for each one, and then we plotted all those averages on a chart. What you'd start to see is this beautiful, predictable pattern emerging. Most of the sample averages would pile up right there in the middle, around the true value, and you'd see fewer and fewer of them out at the extremes. This predictable shape, this pattern, has a name. It's called the sampling distribution. It's like a theoretical map that shows us every possible result we could get from a sample and tells us how likely each of those results is. And this is the secret weapon that's going to solve our chocolate machine mystery.
And here's why this is such a game changer. The sampling distribution does 2 incredible things. First, it tells us how our samples are going to behave over the long run. And second, it gives us the power to take just one sample and use it to make a really reliable mathematical statement about the entire population.
Okay, so this is all really cool in theory, but how does this abstract idea actually help us back in the factory with our real-world problem?
Because let's be honest, in the real world, you can't take thousands of samples. It would cost too much time, too much money. You only get one. You get one shot to get it right. But because we know the theoretical shape of that sampling distribution, we can use that knowledge to our advantage.
And this is what we get to do. By understanding the sampling distribution, we can take our single result of 4.9 grams and we can build what's called a confidence interval around it. This lets us say something incredibly powerful, like this. We are 95% confident that the true average of all the chocolate bars is somewhere between 4.85 and 4.95 grams. Notice we're not 100% certain, but now we can actually measure our uncertainty.
And with this tool, we can finally crack the case. Instead of jumping to conclusions with our 4.9 gram sample, we can now ask a much smarter question. We can ask, okay, if the machine was working perfectly at 5 grams, what are the odds we'd get a sample as low as 4.9, just by random luck? And that lets us make a decision with a known level of statistical confidence.
And really, this brings us to the final big idea here. The world is messy. Data is all over the place. Every poll you see, every scientific experiment, every sample tells a slightly different story. But the beautiful thing is that hidden inside all that randomness are these predictable patterns that let us find meaning and make confident choices in a world of uncertainty. The only real question left is, how much uncertainty are you comfortable with?